So let's try and put all this together, and I've got a pretty fancy looking question here, and I'm going to try and help you interpret what it means. So the first thing is we're given a function, which is the f4 minus 4x minus x cubed, and we're asked to do the antiderivative. That's what this symbol here means, between with these little zeros and twos on the top and bottom. So let's first start by making a diagram of what we've got. We've got a function, and if I factor it, it'll help me graph it. So I've got x and 2 minus x and 2 plus x. So I've got three roots, one at 0, one at 2, and one at negative 2. And the function will look something like this. And if I was to now ask, what is the area underneath the curve between 0 and 2 and the x-axis, this is the area under the curve. Now the beautiful thing is that the antiderivative, or the integral, does that for us. It actually calculates the area under the curve. So why does it do that? Or what is the link? And although I'm not going to go over a formal proof, you'll have to save that for a more advanced calculus class, or you can read up on it in your textbook. But if I wanted to calculate the area of the yellow shaded area, notice that it's not a shape that I recognize. It's not a circle or a square, but I can estimate it by making a whole bunch of little rectangles. And if I add up all of those rectangles, I would get pretty close to the area under the curve. And the skinnier the rectangle, the more accurate the area. So the area under the curve could be estimated at the sum of all the rectangles. And how do I find the sum? So I'm going to use my symbol for sum, which is this, and I'm going to find the area of a single rectangle. So let's take a single rectangle, maybe make it in green right here, and say, all right, how do I calculate the area of a single one? Well, that green one is a rectangle, so it's length times width, and the length of it I'm going to call dx, or the width, maybe I should call the width dx. So that's how wide it is, very tiny. So the width is dx. How long is it? Which means this distance. Well, that's just the y value of the function. And the y value of the function is defined by this. So the length is defined as 4x minus x cubed. So notice there's my expression for area. And now if I take the limit of, make this go really small, so I take the limit as dx goes towards 0, then and add them all up. So I'm adding up the limit as dx goes to 0 of each of the areas, which is 4x minus x cubed over dx. That equals the sum, and this is the integral symbol, antiderivative of the function. So this link still might be a little bit vague, but that's basically what the antiderivative does. It adds up all the areas, infinitely small rectangles, and gets the area. And we know we've practiced how to take the antiderivative. So let's do that now. And the antiderivative of 4x is 4x squared over 2 minus x to the 4th over 4 plus a constant. And what we're going to do is evaluate that expression, so the area between 0 and 2. So that means evaluate it at 0, evaluate it at 2, and subtract the 2, and we should get the yellow area. So I'm going to plug in my value for 2. So 4 over 2 squared over 2 minus 2 to the 4th over 4 plus c. So there's my integral at 2, and then I'm going to subtract the integral at evaluated at 0. So what we're doing is taking the 2 and subtracting the integral at evaluated at 0. So I'm going to plug in 0, and I get 0 minus 0 plus c. Notice the c's will cancel in this expression, and they always will. So this is called a definite integral, and when you're doing definite integrals, the c's are going to cancel every single time, so we do not usually write them. Now I'm still going to simplify the expression here, and I'm kind of running out of room, but lets me help with by making it maybe a different color. So this is 4 times 4 divided by 2, which is 8, and 2 to the 4th over 4 is 4, so this is 4. So the area under the curve between 0 and 2 is equal to 4. That's what integrals do, and let's take a second look at this same equation now and predict what would happen if we changed these values right here. So I'm going to insert a new page. I'm actually going to regraph my function. So my question is, what do you think would be the integral between -2 and 0 of the same function? So if we think of it as interpreting what it means in terms of area, between -2 and 0, so that's between here and here. So we're looking at that area. Well, we already calculated this area. This area was 4, I believe it was. I'm just going to double check here. What was it? Yes, it was 4. So this area is the same. They're symmetrical, so it also has to be 4. But we have to indicate somehow that one is above the x-axis, one is below the x-axis. So this one actually has an area of -4, or an integral of -4. And you could try that by taking the integral and evaluating at -2 and 0 and subtracting, and we're going to do more of that in future. But for now I just want to concentrate on the link between the area and the integral. So let's do one more, and I'm going to take the same function, getting rougher and rougher with my diagrams. So here is my diagram, and the function was 4x minus x cubed, and if I take the integral between -2 and 2 this time, so what happens then? So what happens is I'm going to take the area of all of these and the area of this. Now they're the same, but this one is negative and this one is positive. So when you add the areas together, you're going to get an integral that's equal to 0. So we're going to explore that just a little bit more in next videos.